Okay, let's begin. So we have been looking at the switch capacitor circuits, and in the last class we saw what will happen if we use an OTA instead of an op amp in the circuits. So let me copy paste. I don't want to draw the circuit again and again. We have it anywhere. Yeah. Yeah. Screen. So we saw that if you use an OTA, although the OTA itself might have infinite gain across frequencies, the moment you put it in feedback like this, the feedback capacitors and the load will start loading the OTA, and the voltage gain from the input to the output node will drop. So the OTA cannot respond instantly and change the output voltage. There will be an exponential settling, and the time constant will indeed depend on the GM, right? And also, if you recollect, in phase 1 we charge the capacitor to V in, and when we connect the capacitor like this in phase 2, what happened to this voltage? No, it becomes zero eventually, but instantaneously what happened to that voltage? You remember it? Yeah, at least if the load capacitor was not there, the capacitor voltages couldn't change abruptly. So whatever voltage was stored here will be there at the beginning of the phase 2. So this will jump to minus V. Okay. And we also saw the effect of slowing. Okay, so let's continue. I just want to make a couple of minor points here. So please remember that in practice, these guys will be powered by a single supply VDD, and the lower rail will be ground. And the most common implementation for the first stage of this OTA is usually the differential pair. This will be the basic structure, at least for the input side. So let us say this is the minus side and this is the plus input. So right now we have connected the positive input to ground, right? So if I connect this guy to ground, will this be fine? If I connect this to ground, what will happen to the transistor? Yeah, it's not properly biased, right? So we should not connect it to ground. So what should you connect it to? Yeah, we connect it to some bias voltage, and usually that's a common mode equal to half the supply rail. So this is no longer ground, should be VCM. And remember, even the input you don't give it directly, we add a common mode on top of this. And now the input is charged to VCM plus V in. So the moment I put it in this phase, what will happen to this voltage? It will go to minus of this guy, right? Roughly this. But again, which means a negative terminal, the gate voltage of this guy goes to a negative voltage. It's not that's not great, right? And that's happening because if you think about it, we want the circuit to respond only to the signal V in, right? But it is also responding to VCM here. So we shouldn't sample VCM plus V in across capacitor. So what should you sample? Only V in has to be sampled. So what will I change? Okay, when it's sampling, what's happening here? Here VCM plus V in capacitor, and this is connected to ground. So if I had to sample only V in, what should I do? Yeah, but here if I want this voltage to be just V in, no, something simpler. Yeah, if I make this VCM, we are set, right? So this guy will connect to VCM. So now the capacitor charges to VCM, so this will again jump to minus VCM, which is still not great, right? This will still jump to minus V in, that is also not great. So it is good that it is responding to only the signal, but we have to add the DC bias or the common mode on top of this also. So this is what we want the voltage to jump to. So what will be the change you make? So again, if you think about it, since we are connecting it to ground, this jumps to minus V in. If I raise this to VCM, this will also jump rise by that voltage. So we'll do this. By the same token, usually all the things that are connected to ground are usually the common mode. when we are drawing it as ground, it just meant that in small signal it was ground. Okay, great. So yeah, now we can have, I mean, in practice we have all fully differential circuits, and this will be the fully differential circuit. I didn't want to waste time by drawing, so I already drew it. So same thing, we have two differential halves, and the OTA will be a fully differential OTA like this. So this will be plus and negative, and the input is again fed as VCM plus some delta V by 2. And in the last class we looked at the noise or the mean squared noise for a single-ended implementation, and let's say that was some n naught mean squared noise. For a fully differential case, what do you think the mean squared noise will be? Huh? 2 times? I mean, without going to a lot of details, you have twice the number of switches, twice the number of noise sources, and this part and this part are completely uncorrelated with respect to noise. So the noise power simply adds up. So for a differential case, it will be 2 times n. Okay. So yeah, other minor thing I want to clarify is, so yeah, the way we have is, again, this is all powered from VDD and 0. So the common mode is around the supply rail, I mean around the mid supply VDD by 2. So one of the inputs is going above VCM, other input is going below VCM, right? That's how we are applying. So if one input does this, the other input will basically do this. Okay. So let's say this is our VCM plus delta V in by 2. So what is the minimum value this delta V by 2 can take? No, here this is our VCM plus delta V by 2. What is the minimum delta V by 2 I can have? I have here, what is the minimum voltage I can go? No. What is the minimum voltage I can go from here? Minimum? Huh? Yeah, that's what. VCM minus, this is the thing, right? Input is delta VCM plus delta V by 2, right? So on top of VCM, we can go top and bottom. What is the bottommost I can go to? So which means what is the minimum delta V by 2? Minus VDD by 2. So it can go to minus VDD by 2, and the maximum it can go is, so maximum I can go here, and that will mean an increase by, right? So the fully, I mean the differential signal delta V, what will be its range? Yeah, delta V by 2 goes in this range, so delta V goes from minus VDD to plus, right? I mean, that's why even though we have a single-ended supply, for a differential case we can have minus VDD to plus VDD. So for the single-ended case, what is the peak-to-peak swing we can have? This is a single-ended signal. What is the maximum peak-to-peak sinusoid I can apply? VDD. So this is the maximum sinusoid I can apply. Peak-to-peak is VDD. So peak-to-peak is VDD. So if I were to write the peak-to-peak differential, what will be that? 2 VDD. Okay. Great. So yeah, now we have seen about how to sample the signal, what kind of switches to use, how to design the switches, and how to process those sample signals using switch cap circuits, and how to tackle non-idealities in the op-amps and stuff. So it's time to move on to the next phase. So after sampling, what are we supposed to do? You have to quantize. And if you think about it, quantization basically takes the input, compares it with a bunch of reference voltages, and decides if the difference is greater than 0 or less than 0. So the heart of the quantization operation is this comparator. I'll again draw a differential version. So if this is V1 and V2, difference is delta V. If delta V is greater than 0, one of them will go to VDD, other will go to 0. If delta V is less than 0, this will be 0, this will be 0. We just want to, outputs. Great. So what is the simplest way to realize this? I mean, think about it. What we want to do, we have to sense a small difference and increase the difference to a large by a large amount. Yeah, we have to increase the difference by a large amount so that it saturates to supply or ground. So in principle, if we have an amplifier, right? Let's say with the gain of A, let's say this is delta V. Again, we'll apply VCM plus delta V by 2 like this. So if this is my V out will be A times delta V, and we hope that if this guy is large enough, this might reach VDD. Similarly, if it's small enough, this will go to ground. Fine. So yeah, so if this is the case, what is the minimum delta V I can apply to the circuit so that I can get an output of VDD? No, right? See, now what we are doing is we are applying delta V. The output is ideally A times delta V. The hope is this is large enough that it saturates to VDD. So what is the minimum delta V I can apply? VDD by A. That fine? So this is the minimum input for which I can get VDD. Less than this, it might not reach VDD, at least ideally. Right? And what is the simplest amplifier, differential amplifier? I'm sure this is fine. I mean, you don't even have to think that complicated, right? We have a differential output. The differential pair is this. What is the simplest thing I can put at the drain? I mean, we want a differential output, so we can't put a current mirror. We can put two resistors at the drain, and that should work ideally, right? So let's say I do this. So let's say this is VCM plus delta V by 2. So this is V1 and this is V2. So if this is R and if I call this as output, so what is the output? What is the gain of the circuit? Assume that there is no R0 for the transistors and all. So what is the gain? GM times R. Okay. So I mean, it's okay if you don't remember. It's okay. GM times R times delta V will be the output. Fine. Let me move on to the page. So let us say the output is initially 0, okay, and at this point I apply the input. I expect that the output should go to this, right? Let's say the input is delta V. So if I apply the input at this point, will the output instantaneously jump to this guy? What will happen? Will it jump instantaneously or what will happen? Let's say that's not a problem right now. In practice, what do you think will happen if I do this? Assume that current limitation is not a problem. Huh? You'll have parasitic capacitors at every node, right? So you have parasitic capacitors at the output. So what will happen now? You can only exponentially charge, right? Because we want to charge a capacitor, we can't instantaneously charge the capacitor voltage to anything you want. So it will slowly rise like this. And what is if I had to write an expression for this, how will it look like? For this exponential settling behavior, if I had to write a closed form expression, GMR delta V, fine? That's all right. Okay, it's okay. Let's not take so strict on times. And the time constant is basically the R times the output parasitic capacitance we have, fine? And you can straight away see that this is actually really slow, right? So if I were to increase the speed here, what would you choose for tau? Ideally, if tau is 0, we are all set, but we can't have tau 0 because capacitor is there. And in principle, the gain is gm times r, right? You want the gain to be large. So you can't have tau to be 0. Is that clear? Tau is RC, C is there, and you want large R to get a large gain. So which means I can't touch the magnitude of tau. Okay? So I mean, now just hypothetically speaking, if I can't touch the magnitude of tau, what can I change? Don't forget about the practicalities. No, that's what, forget about practicalities. I mean, GM doesn't imply, I mean, GM doesn't play a role, right? Tau is what is affecting our settling. I mean, whatever it is, it will still be exponential, right? You can't, exponential settling is slow. Ideally, if you have tau to 0, it works, but like we told, we can't touch the magnitude of tau. So just, what is the other thing you can change? We have to change tau. We can't change its magnitude. What is the other thing you can change? Huh? I mean, it's a real number, right? So what is phase? It's a real number. If I can't change its magnitude, what is the other thing I can change? Yeah, but what is the other thing? It's a real number. Let's say tau is a real number. Besides magnitude, what is the other information it has? Let's say this is the real number axis, this is 0. So right now you are choosing only here. Is there something else you can do? I mean, principle, let's say what, I mean, this is the other, that's the only thing you have, right? Only leeway we have. So if tau is less than 0, hypothetically, let's say we can make it, right? And here, we can't make capacitance to be negative because capacitance is already there. The resistor is what we are going and putting. So in principle, let us say somehow we can put a negative resistor, let's see what happens. So now I am going to replace R with negative R. So what will happen to this guy? It's minus GMR delta V, 1 minus e power till plus t by some tau, right? So if I rewrite this is GMR delta V. So if I had to sketch this, how will it look like? It's an exponential increase. So we'll just do this, right? So we have to draw in a different color. So we'll just do this, and eventually it will settle to VDD here. So this at least seems to be much quicker than anything else you have. This is the closest approximation you can get for this step, in practice at least. But that means that we'll have to put some kind of a negative resistor here. There is no physical resistor, this is negative. So let's see if we can emulate something which is negative. Delete this. So first let's understand what a negative resistor means. So we have a minus R. We apply a test voltage. What will be the current in this direction? Minus Vt by R. So which means current in this direction is? So which means that, I mean, if I apply voltage, I should not be drawing current. I should be putting in current in that node. That's what negative resistor means. So hypothetically speaking, if I have Vt, all I want is to push in a current Vt by R. So if I were to take a current source here of value Vt by R, exactly find a current source with this value and put it. For this value of Vt, it will work. But of course, if Vt changes, this will not work. So I can't have a constant current source here. What kind of current source I should have? No. I mean, if it's a constant current, it doesn't work. I should have some kind of voltage controlled current source whose current depends on this guy. So this, let's say, is a voltage controlled current source. I should have something like this. So I'm connecting Vt here. So what should I connect to the controlling terminal? What do I want this current to be? It should be proportional to Vt, right? So what should I connect this to? No. Look at the current, right, in this direction. Huh? No, forget about the drain gate, right? This is just a hypothetical VCCS. This is the controlling terminal. The current here is proportional to some GM times, let's say this is Vx. I want this current to be what? Yeah, this current should be proportional to Vt. So what should I connect this to? Vt. If I do this, it is fine. So uh, what is the simplest voltage controlled current source you know? MOSFET. So if I take a MOSFET, the difference is current flows in the opposite direction here. So this is gate, drain and source. So here again I am putting the V-test. So here this is Vx, so it will be Gm times Vx here. So if I were to connect this directly, we'll be taking the current in the opposite direction. So I want the current to flow in this direction. So what will I connect this to? If I connect it to minus Vt, if I somehow fix it to minus Vt, then the current here will be minus GmVt. So it means current flowing up is GmVt, we get a negative resistor. Fine. So what I'll have to do is to replace these guys with a MOSFET like this. I'll remove the parasitic capacitors. I'll remove everything. Yeah, they will come to that. So we are going to connect that MOSFET to VDD, right? So what kind of transistor I can put? PMOS. So I'll do this. And remember that if the drain is at Vt, what should I connect the gate to? Minus Vt. So here I have connected drain to something. I should connect the gate to negative of this guy. Is there some voltage here which is negative of this voltage? Remember that this is a fully differential circuit. So whatever here, the negative version is here. So I should connect the gate to here. Similarly, I'll have to put another PMOS here. Okay. Great. So if I do this in principle, it should work. So let's see what happens. Yeah. So here, if you think about it, let us say initially I call this Vx and Y. Let us say. Initially, let us say Vx and Y both are equal, and we apply the input somewhere here. Okay. So, and I'll assume that delta V is greater than 0. So we'll have currents in these two transistors. Let us say this is I1 and this is I2. What will be greater? I1 will be greater or I2 will be greater? I1 will be greater. Remember that we had a parasitic capacitors at these nodes. Now we are drawing currents from these capacitors. What will happen to the output voltage? We are pulling out currents from these nodes, right? So voltage should eventually drop. So and they will drop, but which of the two voltages will drop faster? Vx will drop faster. So Vx will do this. This is X and Y. Now if Vx starts to drop, gate voltage of this PMOS transistor is reducing. So what can you say about the current in this transistor? Current will increase, and beyond some point the current here will be much larger than the current you are pulling out. So then what will happen to this voltage? VA will start to increase. Is that clear? So let's say it will do this, and beyond some point VA will start to increase. And if VA increases, what will happen to this gate? That will also increase. So the current here, so we are pushing in lesser current than we are pulling out here. Vx will drop further. So eventually Vx will drop further like this, and so once this will go to VDD. So Y will go to VDD. And this is where we have the e power plus t by tau behavior. Okay. And this kind of exponential increase is usually called regeneration. Okay. Another thing to notice, if here let us say Vx is dropping, we just saw that the gate voltage is reducing, current here is, so current here increases. So what can you say about Vy? I mean, if current here increases, what can you say about Vy? We just saw, right? No, I mean, I don't understand. Okay, see, Vx is reducing, gate voltage of PMOS is reducing. Current in the transistor, what happens to the current? Right, so if the current in the transistor increases, we are pushing in more current into that node. What will happen to that node voltage? It will increase. Is that clear? If Vy increases, again, this is again connected like this. Gate voltage of this is reducing, which means the current in this transistor, will it increase or reduce? It will decrease. If the current we are pushing into that node decreases, what happens to this voltage? It will decrease further, so it will decrease further. So what kind of feedback do you think this is? We started by reducing the node voltage Vx, and the feedback is also enforcing the same thing. So this is indeed a positive feedback. And in this case, we are actually using positive feedback to help us. So if initially the voltage is reducing, we try to reduce it further and further and make it go to 0. Similarly, if one voltage is increasing, we increase it further and further and make it set to VDD. Okay. So this as such has some issues. Let's look at that. So let us say I apply delta V greater than 0 till this time instant. For delta V greater than 0, Vx is at 0, Vy is at VDD. So let us say this is VDD, this is 0. So this is Vx, this is VDD. So this is Vy, right? And here delta V is greater than 0. Now let us say here I make delta V less than 0. Now for delta V less than 0, what do you want Vy to? Vy should go down. So basically what you want is, you want this guy to reduce to 0 and this guy to increase to VDD, right? But as you see here, we have a positive feedback here that is trying to set these voltages to VDD and 0. Once you have set that to 0 and VDD, the positive feedback will reinforce that voltage and try to keep it at the same, right? Because you see that the moment this tries to drop or something, this will aid that and it will make it go to 0 and this will be at VDD. So here the positive feedback is trying to keep this at the same state, and you are trying to change the state by using these guys. So unless the current you are drawing out of this node is much stronger, you cannot pull this voltage down to 0. Is that right? So that is kind of a conflicting case, and it can so happen that you might easily make an erroneous decision if this is not strong enough, right? So this is not a great situation to have, and the reason we are having this situation is, even after finishing the comparison in the previous input, we are retaining the same output state and starting a fresh comparison with the same state. So what do you think we can do? Yeah, basically the thing is, we have to reset both of them to some value. Fine. Before starting, after your comparison for the previous input is over, you clear its state, reset it and start afresh. And here you can do it because if you think about it, we have total time of 0 to Ts, in which half the time we are dedicating it for sampling and only this remaining half is dedicated for regeneration, right? So here is when the comparator is active. Let us say it is phi C. So this is phi C bar. So I can actually go ahead and reset my outputs in this phase. Okay. So what we'll do is this. Yeah, so we'll put some switches. I'll erase this. And we'll reset to VDD. So why not to ground? I'll come to that later. And what should be the control for the switches? What clock? From here, what is the clock phase at which I should reset? I mean, I've written two clocks, phi C bar and phi C, right? In which phase I should reset? Phi C bar. And similarly, even this guy need not be actually active when we are resetting this, right? Isn't it? So you can even turn this guy off by turning this guy off. You don't need to unnecessarily draw current all the time. Only when we are activating the comparator, we will draw current. So even this will clock it at 5C like this. Sorry? Which one? That was initially at 0, let us say. Yeah. That's what. After, let's say, this is here you will have a regeneration phase, right? So once this is done, you are coming to this phase where 5C is 0. So this will be cut off, right? And then you are pulling this to VDD. So this part is not active now. When we are resetting, that's why you want to disconnect the actual differential pair. Okay. So what kind of switch I can use for this? PMOS. So I'll quickly replace with PMOS. So what should be the control for this? Should be 5C. So similarly this. So but let's say instead of resetting to VDD, what happens if I reset to ground? That's also a reasonable thing. I just want both voltages to start from the same. So if I reset it to ground, what will happen? Yeah, if I reset to ground, basically this is the PMOS. I am connecting this to ground, this also to ground. So now we see that the PMOS is on and we have a direct path from VDD to ground. We are unnecessarily burning current from VDD, right? In this case, we don't have to spend current, so that's why it's better to reset to VDD, not to ground. That will keep the circuit off. Okay, great. So now, although this is looking nice, or before going to that, let's actually quickly see how the voltages will change here. So let us say this is 5C 0 and 5C is made 1 here, and we'll consider a case where delta V is greater than 0 again. So in 5C 0, what can you say about the outputs X and Y? In 5C 0, what happens to the outputs? They are at VDD. So I'll maybe draw with this guy. So this is both X and Y. And when 5C is made active, this guy is on, these switches are off. Okay. So since the switches are off, I'll basically remove this. Fine. We'll have currents drawn in these two transistors. And again, I1 is greater than I2. So which node will, so what will happen to these nodes? It will start to decrease, and before that, let me see, there is always parasitic capacitors here. And to start with, both the nodes are at VDD. So what can you say about these transistors? They'll be cut off because for this PMOS, the source is at VDD, gate is also at VDD. Same is the case for the other. So initially both PMOS transistors are off, right? And the only part active is this guy. And this guy is drawing currents I1 and I2 out of the output nodes. So what will happen to the outputs? It will keep dropping, and which will drop faster? X will drop faster. This is Y. Okay. And if X and Y starts to drop, what will happen later? Yeah, but something else will happen. Initially the PMOS was off, but will the PMOS? We want the PMOS to be on. That's the whole point. So when will the PMOS transistor turn on? When one of the gates drops to VDD minus VTH, the PMOS turns on. So which is dropping faster, X or Y? So which left side PMOS will turn on first, or right side PMOS will turn on? Right side PMOS will turn on. So which means we'll start pumping in more current into that node. And once you start pumping in more current into that node, what will happen? Vy will start to increase. So let's say at this point, we have this, and then Vy starts to increase and Vx goes to 1. Okay. So this is what will happen. Now this as such is a nice circuit, but there is one major issue. This is the following. So let us say this is the thing. If you notice, we have finished our comparison here itself, right? And at this point, Vy is VDD and Vx is 0, right? So let us say this is 0, this is VDD. I'll erase these guys. Okay, I'll erase the capacitors also for now. Now this is VDD. So what about what can you say about this transistor? That is off. For now, I'll erase this. It's not in the picture. What can you say about this transistor? That gate voltage is 0. Okay. So now let us say I take some number. So let's say this is some 1.2 volts VDD. Common mode is 0.6 volts. I'll write in millivolt, 600 millivolt. And let's say delta V by 2 some 10 millivolt. So this is 610. So this is 600 millivolts minus 10 millivolts, which is 590. So now if you see, we have applied a gate voltage of around 590 millivolt to this guy. So this transistor, do you think it might be on or off? It will be on. I mean, if you think about it, this pull to ground. So this voltage is as good as ground, right? So this transistor will most likely be on, and this transistor is also on. So we'll have a direct path for the current to flow here, okay? And you're burning power here in this case. Fine. So the point I'm making is, even after you finish making the comparison, which is at this point. At this point, you have finished making comparison. There is no need for you to burn power in principle. But even after you finish it, you are still burning power in this time. Okay. So here we have an unnecessary static power consumption. Even though the inputs are not changing, outputs are not changing, you are unnecessarily burning power. And if you think about it, this will not be a problem if the differential input is very large. So say for example, the delta V by 2 is say 500 millivolts. So this will be 1.1 volt. Here it will be 600 millivolt minus 500 millivolts. This will just be 100 millivolt. So for a small gate voltage, this transistor will be on or off. So if the delta V is large, this is not a problem. This will be off, we are okay. But for small delta V's, it will easily happen that we have a direct path from VDD to ground and we'll have static power consumption. So let's try to solve this. For that, I'll have to copy some circuit. Yeah, maybe I'll copy this. Yeah, I'll erase all this. So if you think about it, the main problem is happening because in this case, this transistor is on and this was also on, and we are connecting these two guys together. And that is what is giving the path to ground, right? So if I don't want to create a path from VDD to ground, what should I do? Right now the problem is happening because both the PMOS and NMOS are connected like this, and that is why we are having this path. If I were to remove this path from VDD to ground, what should I do? Basically, I should not have this connection. I should somehow break it. Simple. So I should not connect these two like this. I should in principle put something here. Okay. So let's call this some element A and B. We don't know what that is yet. And remember that if we, let's say B, this guy should not be conducting when this is 0. When this is 0, this PMOS is on, remember? And that is when we don't want this path. Right? So we want B to be off when Vx is 0. Fine. Now let's look at the element A. So for A, remember that we want Vx to be 0. So we want this path to be on. Right? Only then this node is pulled to ground. Right? But A, so which means A must be on when Vy is VDD. So when this guy is VDD, you want this path to be on. Is that clear? So what kind of an element do you think will do this? An NMOS transistor with gate connected to Vx and Vy will do this. So I'll go and replace these guys with NMOS transistors. I'll have to make some space. And this was the element B. For element B, the control must be Vx, right? So the gate, I have to connect it to Vx. So we'll have another cross coupling. Similarly for the other guy. So the moment you do this, we'll basically break the path from VDD to ground once the comparison is done, and so we'll not have any static power consumption. Is that okay? So now something should strike you. If you look at, let us say, the left half of the circuit, you have one PMOS, one NMOS. If I draw this, the gate of the PMOS and the gate of the NMOS, they are connected. What can you say about the drains of the PMOS and NMOS? They are also connected. So does this remind you of some other element you know? You have a NMOS and a PMOS transistor. Gates are connected, drains are connected. It's a CMOS inverter, right? Everyone knows this, right? I'm hoping you guys know. Gates and drains are connected, so that's a CMOS inverter. So this other way to draw it neatly is as follows. So we draw, put a CMOS inverter. And the output of one inverter, which is this guy, is connected as the input of the other inverter, and vice versa. Fine. So we'll basically connect output of one inverter to the input of the other, and then you have the differential pair. And remember, this was clocked at 5C, and we are also resetting the output nodes, remember, right? So we should have switches there. Resetting the output nodes to VDD. So I can call this X and Y. So this, let's say, call it P and Q, these nodes. So this is our final circuit, and this is called the StrongARM latch. If you think that this has something to do with honoring Neil Armstrong, you are absolutely wrong. It turns out the guy who came up with the circuit, his name is Kobayashi. So he was in Toshiba, and he came up with the circuit, but later some other company used this in their microprocessor, and that microprocessor name was StrongARM. So people started to call it StrongARM latch. So life lesson: if you come up with something new, name it after you immediately. Only then history books will remember you. Huh? Okay. So there is, in practice, there is also one minor modification done. Along with resetting X and Y, we also reset these nodes to VDD. I will not explain the reasons. I can refer you to resources. Otherwise, the circuit is same. Not really, because since we are cutting this off, NMOS will be off. It turns out that this has some issues with dynamic offset. I don't want to cover it. This modification was done later, I think by Razavi, I'm not sure. Yeah. So now let's actually see how the outputs are going to change. Again, I'll consider V1 minus V2 is delta V for now. As usual, is greater than 0. And when phi c is 0, what can you say about X, Y, P and Q? When the clock phi c is 0, Vx, sorry, all the voltages X, Y, P and Q, all of them are reset to VDD, right? So, and when phi C is on, these switches are not active. So I'll remove this for now to reduce clutter. Okay. Yeah, okay. Erase this. So let's say this is when phi C is made active. So here phi C is 0. So at this point I know that if I call it, this is VDD, this is let's say VP and Q. So similarly I am drawing VXY. Fine. Great. At this point I am making phi C equal to 1. So initially these nodes were charged to VDD. Same is the case with these nodes. So what can you say about these NMOS transistors? They'll be off because their gates are at VDD, source is also at VDD. What is the case with the PMOS transistors? They'll also be off because again the source is at VDD, gate is also at VDD. So again, as usual, in the initial phase only this guy is active. So if delta V is 0, we'll again be drawing, if delta V is greater than 0, we'll be drawing currents here and I1 will be greater than I2. So what can you say about these voltages? They'll start to drop. So V, P and Q will start to drop and P will drop faster than Q. So in that case, what can you say about X and Y? If they have to drop, this NMOS must be drawing currents. But is the NMOS transistor on or off? Why is it be on? This source is starting at VDD. No, this is also at VDD. So initially, the NMOS transistors will be off. So no current is drawn out of these nodes, right? So what can you say about X and Y? They will be at VDD. Remember that this is all happening because you have parasitic capacitors at every node, right? So we are just drawing current out of these capacitors now, right? And these transistors are still off. So the output voltages X and Y will still be at VDD. So this is the phase when only the diff pair is on. Now if P and Q starts falling, after some time what will happen? The NMOS will start to turn on, and once the NMOS starts to turn on, what will happen to X and Y? NMOS will start to draw currents and X and Y start to drop. So again, very loosely speaking, let's say at this point this happens, and which of the NMOS will turn on first? This guy will turn on first because P is dropping. So first what will X will start to drop before Y, right? So X will, let's say, start to drop here and Y will drop later, and also X will drop at a faster rate like this, right? And once X and Y start to drop, what will happen to the PMOS transistor? Let's say in this case NMOS was on, right? And this was still at VDD initially. The PMOS transistors, were they on or off? Off, right? And once X and Y start to drop, then the gate voltages for the PMOS are dropping, then they will start to turn on. Okay, and after some time, let us say at this point, the NMOS will start to turn on, and which of the PMOS will start to turn on, and which of the PMOS will turn on? X is dropping faster, this guy will turn on. So this means this will start to pump in current. What will happen to Vy? Vy will increase, and then this will happen in the positive feedback fashion. And so we basically have three different phases. So initially only diff pair is on, and then the NMOS is only on, and finally all of them are on. Great. And let's look at one more thing. I'll probably copy this. Yeah, so let's say I draw the clock phases here, phi c. Let's look at the power consumption here qualitatively. So when phi c is 0, there is no power consumption, right? Because these switches are, these are just connecting this to VDD. Then, and when phi c is made high, when phi c is made high, this guy is active. So for a small amount of time, we'll have currents drawn. And once the regeneration happens, what can you say about the current drawn? Once the outputs regenerate to VDD and ground, is there a direct path from VDD to ground? No, that's the whole point of coming to the circuit. So when phi c is on, initially it will draw current till we have regeneration happening, goes to 0. Right? This is the rising edge, and let's say once phi c falls to 0, but when it falls to 0, what happens? At this point, we are basically trying to pre-charge all these capacitors to VDD. So if you take any node X, we'll have a capacitor, and we are connecting it to VDD through a small on resistance. So what is the current drawn? No, this is basically a case where the parasitic capacitor is there at some node X, let us say. This we are trying to charge it to VDD through a PMOS switch. PMOS switch has an on resistance like this. If I sketch the current, how will it look like? See, at the initially X was, let us say, 0. Assume that X is 0. Initially the current drawn will be what? VDD by R. And once VDD by R, this is VDD by R. Once VDD by R current starts to flow, what will happen to the capacitor voltage? Capacitor voltage will increase, which means the current drawn will drop. You'll have some this. So same thing will happen here also. You'll also have some exponential. So you'll have only power consumptions. When do you have power consumption here? At only the edges of the clock, right? If the clock is static, and if the input is not changing, there is no power consumption. So this truly dynamic circuit, the power consumption is there only if you activate the clock, or which means only when the clock toggles, not even activate. And the other nice thing is you just need one clock phi c. You don't need phi bar and all the business. That makes it a bit simpler. And in practice, of course, there are different varieties of latches. By the way, it's called latch because if you think about it, you have one CMOS inverter here, left side. And if you see, the output of this is connected to the input of other latch. So I can basically draw it like this. And this is indeed connected like this. I'm sure you know that this is the basic structure for a latch. People who have taken 370 might know. So that's why it's called latch. And there are multiple variants of this latches or comparators. And at the heart of them, you will always find either you have a cross-coupled CMOS inverter like this, or a cross-coupled PMOS transistor, or a cross-coupled NMOS. You'll have either of these. And the goal of all these is to emulate the negative resistance to get the regeneration in exponential fashion. So at the heart of all comparators, you'll find one of these, regenerative structures. And in general, these structures are called regenerative latches. So another thing is, if you look at the StrongARM latch, I'll just draw it like this. we are giving the input and taking the output like this. And if this is the clock phi c, when phi c is high is when the latch makes decision, and remember that decision is made somewhere here itself, right? And the output is available only for this time. And when phi c is made low, what happens to the outputs? When phi c is low, what are we doing to the outputs? We are resetting it to VDD. So the digital output is available only in this phase, right? But remember that following this, we'll have some DSP or some digital logic working, and that will expect that the digital bits are available for one whole clock period. So you cannot directly feed this guy. You'll have to store the digital data on something. So what is the thing that stores digital data? Register. I mean, basically a flip-flop or a latch, right? So you can basically put another flip-flop, or for simplicity you can put a latch, and most common put a SR latch. Okay. So yeah, the common thing is to, let's say, have a NAND based or NOR based. So you put an AND or something, and you know that this also has a cross coupling thing. This is a simple SR latch. So let us say here we are connecting the StrongARM latch output. Once the regeneration is done, let us say one of them is at VDD, I'll just say it's logic 1, other is at 0. So what will be the output? Let us say D and D bar, or I think Q and Q bar is a convention. What will happen to Q and Q bar? It's a NAND gate. It's a NAND gate, so if input is 0, what is the output? Output will be 1. So this guy will become 1. And if this is 1, we are NANDing 2 ones, that will be 0. Right? And when the StrongARM latch is reset, remember that both of them will be at 1. So at this point also it shouldn't change. So if both of them are on, what will happen? This is 1, right? This is 0. So if this is 0, this is 1, what will be this? No issues. And this, both of them are 1 here, so this will be 0. Okay. But if you have to use a NOR based structure, remember that the SR latch you can either make using NAND gates or NOR gates. Just a second. Say you make it using NOR. So again, if it is 1 and 0, it's fine. So for a NOR gate, if the input is 1, what is the output? NOR gate is basically OR and take an inversion, so this will be 0. And here you have both inputs as 0 for the NOR gate. Output is 1. It works well here, but if it's reset to VDD, what will happen? This is 0 and 1. It will change. So I cannot directly give this. So basically for a NOR gate, I can't have 1 and 1. You can have 0, 0. So what you have to do is take the StrongARM latch and invert the outputs and give. So you put an inverter so that when the StrongARM latch is reset, the outputs here are 0, 0 and it will retain. Or if you don't want to do it, use a NAND. Great. So yeah, so now we have seen how to make a comparator. We know how to sample signals, so we can start to put things together and make ADCs. So let's start with the simplest structure called the flash ADC. So the idea is simple. First, let's take a single-ended case. We have the input ranging from 0 to VDD. Let us say I want to make a 2-bit ADC. Ideally, I have to compare it with 3 different voltage levels that split the region into 4 regions. And what will be the voltage levels here? Yeah, so it will be VDD by 4, 2 VDD by 4 and 3 VDD by 4. So what I have to do is, how many comparators I need to have then? I have to compare the input with these guys. So how many comparators I need? How many voltages with which I am comparing the input? 3, I'm comparing the input with 3 reference voltages. So how many comparators I'll need? 3, right? So I'll have 3 comparators like this. I'll feed the same input to everything. And the reference voltages must be VDD by 4, 2 VDD by 4 and 3 VDD by 4. So how can I generate it from a single supply VDD? We can put a resistive divider with all equal resistors. I'll put something like this. Okay. This will go here, this will go here. Okay. So for a 2-bit ADC, how many comparators we need? 3. In general, if I have an n-bit flash ADC, how many comparators I'll need? Okay. So if I were to double the resolution, you can see that so not double, if I were to increase the resolution by 1 bit, the number of comparators grows exponentially, and that's why, and for other reasons, we don't use flash ADCs for more than 4 to 5 bits, or at the max 6 bits also, not more than that. Okay. And if you look at the output, remember that I wanted only a 2-bit binary output. I essentially have 3 outputs from the comparators, and let us say the input is lying in this range, 0 to VDD by 4. What will be the outputs of the 3 comparators starting from bottom? This is VDD by 4, right? Input is less than VDD by 4. Output will be what? 0. This comparator is comparing the input with 2 VDD by 4. Input was already less than VDD by 4. This also 0. Fine? Yeah, that's what I'm coming at. Let's see how the output looks like, right? This is how we are getting, right? So if the input is lying in this range, what will be the output? Fine. And in the other range, you'll have like this. So now you see it's no longer a true binary bit, it is some kind of weird output. And in general, if I have an n-bit flash ADC, I'll have 2 power n minus 1 comparators. I'll have 2 power n minus 1 bits like this. Okay. So if you look at a 3-bit ADC, it might be slightly clearer, or maybe it's okay. And this kind of output is called thermometer coded or thermometric bits. I mean, simply because, I don't know if you guys have seen mercury thermometers, it looks like levels rising in a mercury thermometer, right? And yeah, but our all digital circuits work with binary bits, so you have to convert this thermometer to binary. And remember that this is our binary 0, binary 1, binary 2, binary 3. I mean, I'm writing in decimal, but this is what you want. So if you have to convert this to 0, this to 1 and so on, what is the simplest operation you can do? I mean, you see here, right? This is 1 because we have only 1 1. Here we have 2 because we have 2 2s. We have 3 because, we have 3 because we have 3 1s. What is the operation in words? I'm basically counting number of ones. Simplest way to count the number of ones is what? By adding up all the bits, right? So you take the thermometer bits, you give it to an adder, and that will give us the binary bits. Yeah, but the output is, see, this is 2 power n minus 1 bits, output is only n bits. Yeah, it's okay. Yeah. I mean, digital circuit is all easy. I mean, just type a code, it gets you for it. You don't have to sit and design. So. Okay, great. So this is single-ended. Let's also look at differential and finish today. So if we have a differential version, the input, I'll say the Vin plus, I'll feed it as VCM plus delta V by 2. Vin minus, I'll feed as VCM minus delta V by 2. And we already saw what is the range for delta V if I am operating from 0 to VDD. What is the differential input range? minus VDD to plus VDD. So let's say this is the range. So I'll have to basically divide this range minus VDD to plus VDD into so many reference levels I want. So let us say these are the reference levels. This is, let us say, VREF1. This is some kth reference and so on. And being a fully differential circuit, even the reference voltages we have to supply in a differential fashion. So we'll have VREF positive for the kth reference and VREF minus for the kth reference. So how do you think I'll feed these guys? If I had a differential input delta V, I was giving the positive and negative inputs like this. Let's say I have a differential reference VREF K. How will I convert it to individual stuff? I mean, simple logic, right? I mean, I have a delta V differential input. To convert into two individual outputs, I was doing this. I have a differential reference some VREF K. How will I split it here? VCM plus VREF K by 2. Fine, that's all. There's nothing. And let's see how we can generate these quickly. And first, let's see how we can generate these voltages if we have both VDD and minus VDD. So let us say I gave you two supplies, plus VDD and minus VDD. How will I generate all these reference voltages? Same resistive ladder I'll put something like this. Okay. So this will give me, I'll say this is some VREF K. So now what I want to get VREF K by 2. What is the simplest thing I can do? If I have the resistors connected between plus VDD minus VDD, I get VREF K. I want this to be VREF K by 2. I'll scale the inputs also. If I scale the input, output scales, right? So if I scale this guy also scales. Let me actually copy this, we'll use it later. So that generates that generates this guy. Now I have to add VCM to this. What is the simplest thing I can do? I'll add VCM here, which means all the voltages will rise by VCM. Fine. So VCM is VDD by 2. So this is ground. Done. So similarly, I'll do the negative side also. For the minus references, now I have plus VREF K by 2. I want minus VREF K by 2. What should I do? If I have inputs VDD by 2 and minus VDD by 2, I get plus VREF K by 2. I want to invert the sign of the output. What will I do? Invert the sign of the input. This is minus. Done. I have to do this. And now I have this guy. I have to add VCM to this. So I'll go and add everything. This is minus. So what happens? This guy is now VDD. This is 0. Okay. Yeah, we usually have to separate things and do it. I mean, ideally, see. Yeah. So basically, as he's pointing out, if we have, let us say, something like this. This is the VREF 1 by 2 plus VCM. In the other ladder, the one from the top is minus VREF 1 by 2 plus VCM. Right? Because you see here, right? This guy which is connected to ground is same as this guy. Sorry, yeah. Resistor is there, use resistor. Since we have resistors, we use resistors. Yeah, resistors. Yeah. Okay. So the differential flash will look like this now. You will have to have two reference ladders like this. So one will be generating the positive references, one will be generating negative references. So remember that if I had a single-ended case, I was comparing input with a kth reference. Now I have a fully differential case. I have a positive input. I'll compare it with a positive reference. This is my one. I'll have to compare this with negative input minus negative reference for k. Okay. I have, let's say, Vn plus. I should get Vn plus minus Vref plus for the kth reference. What is the simplest thing I can put here? Huh? I have Vnp. I want to get Vnp minus some Vref k. What is the simplest thing I can put here? I have to put a voltage source. So now we should be knowing, instead of voltage source, what will you put? A capacitor charged to that voltage. So which means I have to charge the capacitor. So in one phase, I'll go and charge the capacitor to Vref positive k, ECM. And in the other phase, I'll go and connect it like this. Okay, so let's say this is phase 1. Okay. This is for the positive side. Similarly, I'll do for the negative side also. This flipped version. So Vref minus 4k CM 2. So this will give the other side. This is V in M. This one. You work out and check. So okay, I'll give that as an exercise. Please check it out. Why am I connecting this to VCM? Why not ground? Remember that the input I want here is delta V by 2 minus my Vref k by 2. On top of it, I should have VCM. This is the differential portion. This is the differential portion. Okay. So you work out and check. I mean, usually in any circuit, right? Instead of connecting it to ground, you have to connect it to VCM to boost it. That's a simple logic. But yeah, you can work out and check what happens. So these are the two inputs we have. Vref M for kth reference. This will give it to a StrongARM latch or any latch you have. Okay. And if you notice, remove this. In which phase are we sampling the input here? Look at this. In which phase are we sampling the input? First phase. And I have not put an explicit sampling capacitor because in most cases the parasitic gate capacitor here itself will be good enough. I mean, especially in flash, many times, see, as I mentioned, flash has maximum 6 bits. We don't use more than that, right? Now, if I have a sampling capacitor, see in, what does the value of the sampling capacitor determine? If I have a sampling capacitor like this, right? What does the value of the sampling capacitor determine? Or if I increase the capacitor, what changes? But time constant depends on RC, right? Just the C value, is there something that was just dependent on C? The noise was dependent on KT by C, right? So the noise is what will dictate what capacitor you should use. And since for flash ADCs we have 6 bits, what is the signal to noise ratio for 6-bit ADC? Oh, how much is it? Around 37 bits, 37 dB maximum, right? And for this small SNR, you might find that the gate parasitic capacitance itself will be enough to meet your KT by C noise. If not, you can go and put it. Okay. So in phase 1, you will sample it like this, and you compare in phase 2. So the latch will be activated in phase 2. Is that okay? So same thing, I mean, we are going to sample in phase 1 onto the gate parasitic capacitor. In phase 2, I will enable the comparator so that it makes the comparison. And in that phase, I will go and charge this capacitor to my required reference. Okay. So if this I call this CB, how should I choose CB? Is there any constraint on CB, or I can choose any value for CB? What is this CB doing? It is acting like a voltage source for us, trying to hold the charge. So the voltage across CB should not change. So is there any constraint here? Yeah, where can it lose the charge? There should be a path to ground. Where is the path to ground? In phase 2, what's happening? We are connecting it like this. We are charging it, no issues. In phase 1, what's happening? So is there a problem? At the gate, what else you have? You have the parasitic capacitor, right? So how should you choose the capacitor to be then? I mean, if you connect it like this, this capacitor will try to steal some charge here, right? You should make sure that your CB is large enough than your input gate capacitance so that you don't lose the charge. Okay, that's how it is done. And yeah, so finally you have these resistive ladders. You subtract the reference like this and then feed it to the StrongARM latch. And remember, output is given to an SR latch so that you have it for one whole clock cycle. You will have, let us say, 2 power n minus 1 outputs like this. Give it to an adder, and then you get binary outputs. So here you have 2 power n minus 1 bits. So this will be the simplest structure of a flash ADC. This is a StrongARM latch. I am drawing only one-sided. You will have a differential structure. I am just drawing one side. So you generate the references like this using resistive ladders, and these references will basically go here, right, for charging this capacitor. You subtract the input from the reference like this, and then feed that difference to the StrongARM latch. StrongARM latch will make the decision. You will have 2 power n minus 1 such StrongARM latches, and that's a thermometric bit. You add it and get the binary version. I mean, I mentioned that you have 2 power n minus 1 such bits. Yeah, maximum is 2 power n minus 1. But yeah, I mean, if n bits, right? If you have an n bit binary, the maximum you can represent is 2 power n minus 1, right? That's all. We are going to sum up all these guys. At the max, you can have 2 power n minus 1. That can be encoded in n bits. So let's stop.